All right, today we're diving into one of the most beautiful and, frankly, mind-bending results in all of complex analysis, Jensen's theorem. It's this incredible piece of mathematics that shows how a function's deepest secrets, its inner life, are written all over its face.
And this really gets us to the central mystery we're tackling. How on earth can the very specific hidden spots where a function hits zero, deep inside some circle, tell you exactly what its average value is on the edge of that circle? I mean, it sounds kind of like magic, doesn't it? Okay, let's just put it all out there. Here it is, the full equation in all its glory. And yeah, I know it looks like a whole bunch of symbols, it's a little intimidating, but trust me, we're gonna unpack this whole thing piece by piece, and by the end, it's all gonna make perfect sense. So, first up, let's think about this theorem as a kind of perfect balancing act. It finds this amazing equilibrium between what a function is doing on the inside and what it's doing on the outside. You can really see how Jensen's theorem is a tale of two halves. On the left, you've got the interior data, all the juicy stuff from the function's core, like its value at the very center, and crucially, where all its zeros are hiding. And on the right, you've got the boundary data, which is basically its average behavior, way out on the edge of a circle. The theorem is the bridge that connects these two worlds. Now, to really get a feel for that interior side, we can't just use the regular old average we all learned in school. We need something a little different, called the geometric mean. So instead of adding everything up and dividing, you multiply everything together and then take the root. It's perfect for complex functions, because they're often built by multiplying things together. And this is where a cool property of logarithms comes in handy. You see, a sum of logs is actually just the log of a product. So that entire left side of our big equation, it's really just the logarithm of one big multiplication problem. It's a single number that neatly packages up the function's value at the center along with the influence of all of its zeros. It's a geometric mean in disguise. Okay, so we've got the lay of the land. But how in the world do we prove that this incredible balance is actually true? Well, let's walk through what has to be one of the most clever proofs in all of mathematics. The strategy here is just brilliant. It's a classic three-step game plan. First, we're going to solve a much easier version of the problem. We'll look at a function that has no zeros at all. Then, and this is the really cool part, we're going to invent a special mathematical gadget to just get rid of the zeros from any function. And finally, we'll put it all together to crack the whole puzzle wide open. So, step one, let's play on easy mode. Imagine our function, f of z, has absolutely no zeros inside the circle. If that's the case, Jensen's theorem gets way simpler. See, all those extra terms just disappear. It just says the log of the value at the center is the perfect average of the log of the values on the boundary. This is a classic result for super smooth functions called harmonic functions. But of course, that's the simple case. Most of the really interesting functions out there do have zeros. That's what gives them their personality. So this is the real challenge, isn't it? How do we handle those zeros? How do we tweak our simple formula to bring them into the picture? And the answer is just a wonderfully clever trick. Instead of trying to wrangle the zeros directly, we're going to use a brilliant mathematical tool to just make them vanish. And here it is, our secret weapon, the Blaschke factor. Now, I know it looks a little gnarly, but what it does is actually beautifully simple. It's designed with one and only one purpose: to target a zero at a specific location, zj, and cancel it out completely, without messing anything else up. It's like a mathematical zero-seeking missile. Now this property right here is the absolute key that unlocks this entire proof. It's the magic trick. While this factor is busy canceling out a zero on the inside, it has this incredible feature. On the boundary of the circle, its size, its absolute value, is exactly 1. Think about that. It means when we multiply our function by it, the function's size on the boundary doesn't change at all. It's like it's wearing an invisibility cloak, but only on the circle's edge. So here's the plan. We're going to build a brand new function. Let's call it a capital F of z. And we build it by taking our original function, f of z, and then for every single zero it has, we multiply it by one of these Blaschke factors. We're just hitting it with one factor for each zero we want to eliminate. And just look at what we've made. Our new function f of z is perfect. It's the best of both worlds. First, because we hit it with a Blaschke factor for every zero, it is now completely zero-free. We've cleaned it up.
And second, because each of those factors is invisible on the boundary, the size of our new function is exactly the same as our original function all along the edge of the circle.
Okay, this is it, the grand finale. We have our brand new, perfect, zero-free function f of z. So now we can use our simple formula on it and then work our way back to see what it tells us about the original function we started with.
Remember that easy mode formula from the beginning? The one for functions with no zeros? Well, guess what? Our new function f of z has no zeros. So we can just apply that simple formula directly to it. We know for a fact that this equation has to be true for f.
Next up, we have to figure out the value of our new function right at the center, at z equals 0. All we have to do is plug 0 into the big formula we made for f, and when all the math settles, what pops out is the value of our original function, f of 0, times this whole chain of r divided by zj terms, one for every single 0 we zapped away. And now for the big reveal. We take all our pieces and substitute them back in. The right side of the equation for f is identical to the one for f, because their sizes match on the boundary. The left side, that log of f of 0, becomes the log of that whole product we just calculated. And boom! We are right back where we started, looking at that original mystery equation. Only now, it's not a mystery anymore. It's proven.
So, okay, we did it. We walked through the proof, we solved the mystery. It's a really clever bit of math. But so what? Why does this theorem actually matter? What's the big deal? Well, it turns out this is so much more than just a neat formula. It's an absolute powerhouse. It gives us this fundamental link between the tiny, local details of a function, like its zeros, and its big global behavior. And it's a critical tool everywhere. It helps prove the fundamental theorem of algebra, it shows up in number theory when analyzing the famous Riemann zeta function, and it's even used in things like signal processing and engineering.
So if there's one big idea to take away from all of this, it's this. At its very core, Jensen's theorem is telling us something so profound and so simple. The geometric mean of what's happening inside the function is a perfect match for the geometric mean of what's happening on its boundary. The inside and the outside are locked together in this beautiful, multiplicative way.
And that really leaves you with a final big thought, doesn't it? Jensen's theorem pulls back the curtain on a hidden law, connecting the microcosm of a function's interior to the macrocosm of its boundary. It really makes you wonder, what other beautiful, invisible laws like this are out there, connecting the local to the global in patterns we just haven't discovered yet?